Alright, so we've got a differential equation here. We want to find a power series solution of this differential equation, y double prime minus xy prime plus 2y equals 0. We might ask ourselves, why do we need to find a power series solution? Well, usually, if it's not constant coefficient, this x here is not constant, so it's a non-constant coefficient differential equation, and it's not a Cauchy-Euler equation, which we should know how to solve. This type of equation generally is going to be solved using a power series solution. I mean, there are other techniques, but we're just going to solve it using a power series solution expanded about something called an ordinary point, x0 equals 0. An ordinary point is something that's not singular. Well, what's a singular point? A singular point is any point that makes the coefficient of y double prime equal to 0. In this case, there's nothing really that makes it 0, so this is an ordinary point of the differential equation. So if we have an ordinary point of the differential equation, then we guess a solution of this form. Y equals the sum, n goes from 0 to infinity, Cn, x minus 0 to the n. So you put your ordinary point right here, x minus x0. So this is the general form of a power series expanded about, in this case, 0. So we start there and we say, okay, if that's our guess, then y prime, so if y equals the sum, n goes from 0 to infinity, Cn, x to the n, then y prime, differentiate that power series, that goes n equals 0 to infinity, Cn, n, x to the n minus 1. Now, this is really interesting because if we plug in n equals 0, this really becomes C0 times 0, x to the negative 1, plus the sum, n equals 1 to infinity, Cn, n, x to the n minus 1. So now this term, when I plug in n equals 0, is actually just 0. So starting this sum at n equals 1 is no different than starting it at n equals 0. So actually we're just going to write that this is the sum that goes from n equals 1 to infinity, Cn, n, x to the n minus 1. Alright, so we've got y prime. There should be a prime up there, sorry. So we've got y prime. All we got to do now is differentiate that to get y double prime. So we can get y double prime by differentiating one more time. So y double prime would be equal to the sum n equals 1 to infinity, Cn, n times n minus 1, x to the n minus 2. So that same logic is going to apply here whenever we evaluate at n equals 1. This whole term, n equals 1, is going to make this 0. So we can actually start this series at n equals 2. If I plug in n equals 1, I get C1 times 0, x to the negative 1. So that's going to be 0. So actually this is really just the series that starts at n equals 2. So sum n equals 2 to infinity, Cn times n minus 1, x to the n minus 2. So now we're going to sub these three expressions for y prime, y double prime into our differential equation. So now sub these three into our DE differential equation. So sub these three into our differential equation. Well, our differential equation was y double prime minus xy prime plus 2y equals 0. So y double prime, we know, is the sum n equals 2 to infinity, Cn, n times n minus 1, x to the n minus 2, minus x y prime, well, y prime is the sum, n equals 1 to infinity, Cn, n, x to the n minus 1, plus 2 sum, n equals 0 to infinity, Cn, x to the n equals 0. Alright, so now we're just going to do a little simplification, and then we're going to try to combine it into a single series. So we're going to simplify, then try to combine. into a single series. So that's our goal, is to combine this into a single series for which we can find a relationship between the constants. Our whole goal is to find a relationship between the constants and figure out how they're related to each other so that we can write all the terms in relationship to one or two constants. Then we have our series solution. So the first term, it's not going to change. I have no simplifications that can really happen here. I mean, I could multiply n times n minus 1, but it's not really needed. It's not going to help us necessarily. But we can pull in this x to the sum, because x has nothing to do with n. I can pull x in over here to this exponent. I can say x times x to the n minus 1 will be x to the n minus 1 plus 1, because there's a plus 1 right here. Also, we can pull this 2 inside this series here. So we'll rewrite this. We get the sum n equals 2 to infinity cn n times n minus 1 x to the n minus 2 minus the sum n equals 1 to infinity cn n x to the n minus 1 plus 1 plus the sum plus n equals 0 to infinity 2 cn x to the n equals 0. Alright, so we've got a little bit of simplification here, and now we can use a little bit of mathematical magic, and we can say n minus 1 plus 1 is really just n, so we're going to rewrite that. Just erase there. Get that exponent in the middle to just be n. So now we want to combine into a single series. So to combine into a single series, we need same exponent on x in each series, and we need the same starting index for each series. Notice here that this starts at n equals 2, this starts at n equals 1, this starts at n equals 0. So the starting index is really these numbers here. So that's what we mean by we need them to have the same starting index. Furthermore, these don't have the same exponent on x. Here we have n minus 2, here we have n, and here we have n. So these are not the same. We need them to be the same before we can combine them into a single series. So let's rewrite it and then figure out how to combine them or rewrite these so that they have the same index and the same exponent. Alright, so I've just rewritten the series here. What we can do now is what we call re-index the sums. So we're going to re-index the sums. And I liken this to a u substitution for an integral, but it's really just a re-index of the summation by saying, okay, what do I need to let k, we'll say k in this case, we're going to let k be something so that we get x to the k. So we will want x to the k in each term. So x to the k, we're going to make these each x to the k. That's our strategy. So if I want this to become x to the k, I'm going to let k equal n minus 2 for the first sum at least. If k equals n minus 2 in the first sum, then I could say that n would be equal to k plus 2. So if n equals k plus 2, then k equals n minus 2, and I'm going to sub all that n up here. But just like for integral with u substitution, if we have a definite integral, we need to change the bound. So this is going to be the same case here. So if n equals 2, we would get k equals 0, plugging that into our substitution. N equals 2, I get 2 minus 2, k equals 0. So if n equals 2, then k equals 0. If n goes to infinity, then k also goes to infinity. So that's going to be our re-indexing for the first series. So we re-index the first series by saying, okay, this is the sum, k equals 0 to infinity. Now Cn is going to become Ck plus 2. Ck plus 2 times k plus 2 times k plus 2 minus 1, x to the k. Now the next series, we're going to do a different index. We're going to say k equals n, because I just want this to become x to the n, so we're just going to let k equal n. So there's really no re-indexing happening, we're just changing the summation variable. So if k equals 1, or sorry, if n equals 1, then k equals 1. And if n goes to infinity, then k goes to infinity as well. So the second series becomes the sum, k equals 1 to infinity, ck times k, x to the k. And likewise, the last series, we're just going to let k equal n there as well. So nothing really changes for the last series except the letter itself. So it's going to be the sum, k equals 0 to infinity, 2ck, x to the k. And then this whole thing equals 0. Alright, so we've got the same exponent, but we don't have the same starting index. This starts at 0, this starts at 0, this starts at 1. So what we can do is we can break off the k equals 0 term, so evaluate at k equals 0. And same thing down here, we're going to evaluate this one at k equals 0 and rewrite just a little bit. So evaluate at k equals 0. So if we evaluate this at k equals 0, we'll get c2 times 1, or that's actually a 2, so c2 times 2 times 0 plus 2 minus 1 is just 1, x to the 0, plus the series k equals 1 to infinity, so that's the rest of this, ck plus 2 times k plus 2, we'll just rewrite that as k plus 1, x to the k. So that's just that first series rewritten by expanding out the k equals 0 term out front. So this whole series here has just been rewritten right here. I'm not rewriting anything here, I'm just going to leave this one alone for now, and then we're going to break out the k equals 0 term from this last series as well. So k equals 0, get 2c0, x to the 0, plus the sum, k equals 1 to infinity, 2ck, x to the k. Alright, so we're going to rewrite all of this. Now we'll have the series starting at 1 for the first series, starting at 1 for the second series, and then starting at 1 for the third series. We'll just write these constant terms out front. Right, so we've rewritten everything here. We've got these constant terms that were multiplied by x to the 0. We've got these terms now for each series starting at k equals 1, and we have the same exponent. So now we can combine it into a single series. So we get 2 times c0 plus c1 plus the sum, k equals 1 to infinity. We'll put a big bracket here, because we're going to factor out x to the k from each term. Put a big bracket, so we get ck plus 2 times k plus 2 times k plus 1 minus kck plus 2ck. And we factored out x to the k from each term equals 0. Alright, so now we've got something at least in the form of a series for the x to the k terms from k equals 1 to infinity, and then we've got a constant out front. Now by linear independence, so we just need to remember what linear independence is. So linear independence tells us that the coefficients are going to be 0. Linear independence. It says that if we have a constant plus a constant times x plus a constant times x squared plus a constant times x cubed plus so forth equals 0, then the only way that can equal 0 for all values of x is if the constants are equal to 0, or the coefficients are equal to 0. So this constant is going to equal 0, and then these coefficients in the bracket are all going to be 0. So all the coefficients are going to equal 0 due to linear independence. So all coefficients will equal 0 due to linear independence. So that's going to tell us that 2 times C0 plus C1 equals 0. Well, that would just tell us that that should have been a C2, sorry, C2. And so this is a 2. So that tells us that C2 is equal to negative C0. So we got a relationship right here. We want to keep that in mind for later. But C2 is equal to negative C0. And then we want to set the bracket, everything in the bracket equal to 0. So we get CK plus 2 times K plus 2 times K plus 1 minus KCK plus 2CK equals 0. And what we're going to do in general is solve for the larger index, CK plus 2 in this case. We always want to get the larger coefficient in terms of a smaller coefficient, at least as far as indices go. So K is less than K plus 2, so we solve for the larger index. Solve for the larger coefficient index. In this case, CK plus 2, we're going to solve for that term. So once we solve for that term, we will have what we call the recurrence relation. All right, so we've solved for CK plus 2, and we've found our recurrence relation. What we're going to do is try to expand this out to get at least a little bit of an idea of what the solution, in this case we have two solutions, what they actually look like for the power series. So we plug in different values of K to get explicit terms, C3, let's say C3 in terms of C1, and then C4 in terms of C2, and C5 in terms of C3, etc. And try to get some kind of relationship going between these coefficients. So let's start off with K equals 1. If we plug in K equals 1, we get C3 equal to 1 minus 2 over, I'm plugging in K equals 1, so that gives me 2 times 3 C1, which is equal to negative 1, we'll write it this way, over 3 factorial C1. Right, so then plug in K equals 2, see what we get. K equals 2, we'll get C4 is equal to 2 minus 2 over 3 times 4 C2. Well, that's 0 times C2, which is 0 regardless of whatever C2 is. So C4 is 0. So that means every even term, C6, C8, those are all going to depend on C4, but C4 is 0. So this is going to tell us that all even coefficients greater than 2 are equal to 0. So all even coefficients greater than 2 are 0. So all even coefficients greater than 2 are going to be 0. So that's interesting, very interesting actually. So we're only going to plug in terms that are odd now. So plug in K equals 3 and then K equals 5, etc. So K equals 3, we get C5 is equal to, in this case, 3 minus 2 over 4 times 5 C3, which is equal to 1 over 5 times 4. Now we're going to plug in what C3 is. C3 is negative 1 over 3 factorial C1. I can rewrite that as negative 1 over 5 factorial C1. Now it'd be tempting to stop here and say that whatever the index is, that's going to be my factorial, but that's not the case. We'll see that with one more value of K. So when K equals 5, we'll get that C7 is equal to 5 minus 2 over 6 times 7 C5, which is equal to 3 over 7 times 6. And now we plug in what C5 is. It's negative 1 over 5 factorial C1, which is equal to negative 3 over 7 factorial C1. So actually it's not a direct relationship. There's a little bit of an extra term that we'll see even when we plug in C9. We'll see it's going to get an extra 5 up in the numerator. So we'll try to look at that one next. So we plug in k equals 7. If we plug in k equals 7, we'll get C9 is equal to 7 minus 2. 7 minus 2 over 8 times 9 times C7, but that's equal to 5 over 9 times 8 times negative 3 over 7 factorial C1. And that can be written as negative 5 times 3 over 9 factorial C1. So actually this is going to be a little bit of a complicated closed form if we were trying to write this in a closed form, but let's go back to our original solution and expand it out. So our original guess was y equals the sum from 0 to infinity Cn x to the n. Let's expand that out. That's C0 plus C1x plus C2x squared plus C3x cubed plus C4 x to the 4 plus C5 x to the 5th plus C6 x to the 6th plus, you keep going. Now we know all the even terms greater than 4 are going to be 0, so actually we can just forget about all the even terms greater than 4, greater than or equal to 4. So we expand this out, writing in the explicit relationships we know. Well, that's going to be C0 plus C1x minus C0x squared minus 1 over 3 factorial x cubed minus 1 over 5 factorial x to the 5th minus 3 over 7 factorial x to the 7th minus 5 times 3 over 9 factorial x to the 9. And the next one, we're not going to write it, but it would be 7 times 5 times 3 over 11 factorial x to the 11. Now, we can actually factor out some coefficients here. These two terms have a C0 and then the rest have a C1, so this actually does produce a nice two-solution system, 1 minus x squared times C0, and then we get a C1 times x minus 1 over 3 factorial x cubed minus 1 over 5 factorial x to the 5th minus 3 over 7 factorial x to the 7. Let's see, these should have all had a C1, sorry. C1 up here. C1 on each of those terms. Minus 5 times 3 over 9 factorial x to the 9. And so we keep going. Now, when you actually have a real-world implementation of this, you're just going to use the first, I don't know, 3 or 5 terms of your series solution to estimate the actual solution. I mean, it's impractical to use infinitely many terms, so you would just have some truncation error in your solution by cutting off, after maybe we get to the x to the 9th power. So it'd really only use the first 5 terms of the series solution anyway in practicality. So getting a nice closed form notationally is not really worth the overhead or worth the work to get there necessarily. It's not too complicated, but getting a product of the odd numbers based on odd indices is a little, unnecessary. So these would be our solutions. So we could write this as C0 times a first solution, we'll call it y1 of x. So this would be a y1 of x term here, call that y1. And then plus C1 times y2 of x. I could just say that y2 of x is this term here. So this is generally what we talk about whenever we talk about solving differential equations. We have a constant times the first linearly independent solution plus a different constant times the second linearly independent solution, and that's exactly what we've derived here with this power series solution. So this was a really good example for seeing an ordinary point expansion that gives two linearly independent solutions.